Okay. Okay. Can you see my screen?
Yes.
Okay.
眼前的是这样的吗？
对。
也这么大的。
对，可以。
Okay. Okay. Hello everyone. I'm so pleased to make a presentation today. Today I am making a paper review. The paper's title is From ImageNet to Image Classification, Contextualizing Progress on Benchmarks. This paper is published in ICML 2020.
我怎么这么多呢？
First, let me introduce the background. Here is image classification pipeline. The image classification task can be divided into two phases, the training phase and the inference phase. For the training phase, we have designed a model, and the model is trained on a large-scale data set, and then evaluated on the validation set of the data set. In the inference phase, we have an image from the real world and send it into the model trained in the training phase, and the model will give us a prediction. For example, we input the image of a cat, then it will predict it is a cat. So the authors discussed in this paper is how aligned the existing benchmarks with their motivating real-world tasks. Here the benchmarks refers to the ImageNet dataset, which is one of the largest image recognition dataset in the world. The paper is discussed this issue from two perspectives. The first perspective is for the multi-object in the image, because for this paper, for this image, we can see here's a cat, but it also includes the grass and the ground. For the second picture, it includes a lemon, grocery store, tomato, and avocado. And for the third picture, it contains a coffee pot, teapot, cup, and so on. So it cannot be only referred to a single label for these images, but in the ImageNet, the picture in the dataset only have one ground truth label. So the dataset annotations obtained can sometimes be ambiguous, incorrect, and otherwise misaligned with the ground truth. The second perspective is the bias in the label validation, because you can see these three pictures. They are in ImageNet dataset. For us humans, we may label it as missile and stage and monastery. But in the ImageNet, their label are projectile, acoustic guitar, and church. Let's see the second picture. For us humans, we may annotate it as a thin label, like a stage, because the acoustic guitar is not the main object in this picture, but in ImageNet, the label, it is acoustic guitar. Why lead to this this problem? We can have a closer look at ImageNet dataset. This is how ImageNet created. It can be divided into 3 steps. The first step is label collection. In this step, the ImageNet creators first select a set of classes using WordNet hierarchy. So after this step, we can get a set of classes. And then the second step is image collection. In this step, the labels obtained in the first step are sent into search engines. By using the search engine, we can get a lot of the pictures refer to the labels. And in the third step, it is crowdsourced validation step. In this step, the label in the first step and the image in the second step are sent to the cloud sourcing platform, and people are asked to validate whether the label is in the picture. Let's have a example to illustrate this process. We take the Stanfordshire Bull Terrier as example. We first select this label from the WordNet hierarchy, and then we search the label in a large-scale search engine like Flickr. So we can have a lot of pictures for the Stanfordshire Bull Terrier. Then we have label and image, and send it to a crowdsourced platform. The people will to validate whether the picture contains the Stanfordshire Bull Terrier. If it is in the if it is yes, we have get a pair of the image and the label pairs. So the dataset is built in this process. But for some fine-grained classes, it requires a strong knowledge base for the annotators. For example, I do not know what the Staffordshire Bull Terrier look like, so I cannot judge whether it is in this picture. However, even put aside occasional annotator errors, the resulting dataset might not be accurately capture the ground truth. This pipeline design itself can lead to certain semantic errors in the dataset. The author concludes the root cause for these errors in 2 ways. The first one is the images with multiple objects, because annotators are instructed to ignore the presence of other objects when validating a particular ImageNet label for an image. However, these objects could themselves correspond to other ImageNet classes. And the second one is the bias in image filtering. Since annotators have no knowledge of what the other classes are, so they do not have a sense of the granularity of the image features. Moreover, the task itself does not necessarily account for their expertise. This implies that potential error in the collection process. Here's some examples of the images in the ImageNet dataset. For example, for this picture, the ImageNet label is plate, but it also contains the soap bowl and maybe the desk and the soap. And for this picture, the ImageNet label is banana, but it also contains orange and the bowl. So because the ImageNet dataset creation pipeline only to validate whether the label is in the image, so it ignores other objects it maybe contains in this picture. And the second example is about the bias in the image filtering. Because the annotators are not experts, so they cannot recognize whether the dog is the Norwich Terrier or Lakeland Terrier, and also they maybe make mistakes about this mountain. They may validate it as a volcano, but it is up. In order to solve this problem, the authors proposed a data annotation pipeline to evaluate whether the ImageNet dataset can be used to accurately evaluate the model performance. It is the overview of the data annotation pipelines. It contains two phases. The first phase is to obtain the candidate labels, and the second phase is the image classification via classify task. Because asking an untrained annotator to choose from among all 1,000 ImageNet classes is infeasible. To overcome this difficulty, the pipeline contains the two phases. Because the first phase we can get a lot of the candidate labels to reduce the size of the label the annotators need to select, and then they need to select the main object and how many objects is contained in the picture. For analysis, the author used 10,000 images from the ImageNet validation set. That is 10 randomly select image per classes. Then I will introduce the two phases in detail to let you know what they do in detail. In the candidate label obtain phase, the authors first obtain the potential labels for each image by simply combining the top 5 predictions of 10 models from different parts of accuracy spectra term with existing ImageNet label. And take this picture as an example. The picture is predicted by 10 models, and they select the top 5 predictions into this stage. And then the authors reuse the ImageNet content text that ask the annotators whether the picture contains the salamander, and whether the picture contains both the bottle cap, and whether the picture contains the aft, and whether the picture contains park. They asked the annotators for all the potential label and to calculate the selection frequency for these labels. It is the process to get the candidate labels. Here's the model in the red box are the 10 models that the authors used in this phase. They are ImageNet and Inception version 3, and so on. And other models are the comparison models in this paper. Here are the top 1 and top 5 accuracy about this model, of this model. So this image illustrates the how many candidate labels for the images, and the author finds the average potential label for each image is about 14. The second phase is image classification via the classify task. In this task, annotators are asked to identify all labels that correspond to the object in the image, and to select the label for the main object. Moreover, since ImageNet contains classes that could describe parts of the attributes, so the car and the car wheel are regarded as two distinct objects in this process. We can see that the picture is sent into this phase, and these are potential labels. The annotators are to select the whether it is in the picture, and to select the main object in this validated objects. So after we get these labels, we can the authors do a lot of experiments to qualifying the benchmark task alignment of the ImageNet. In the first perspective, they test the multi-object images. The performance of multi-object images. First, let us see how often this additional object appears. We can find that more than 1/5 of the images contains at least 2 objects, and we can see that the pairs of classes are consistently co-occur. What it means, we can find this figure that we find more than 7,000 picture has only one object in the image. Yes, in the image, and more than 1,500 images contains 2 objects, and so on. So in the second figure, we can find when the ImageNet label airliner appears, the percentage that the label wing also appear is 100%. They are always appears together. It's the same for the table lamp. So assign only one label to the image is not appropriate. So they test the model accuracy on multi-object images. First, I will introduce how they measure the performance. The model performance is typically measured using the accuracy with respect to a single ImageNet label, and treat it as ground truth. So for the image, for the first image, the label is monastery, and these three are not the label for this image in the ImageNet dataset. We can find that the performance of the models in the dataset, the black dash means the full test set performance of the model, and the blue line. Okay, can you see? Oh yes. The blue line means all the image 10,000 image performance on this dataset, and the orange line means the performance, the model performance on the images with only one object, and the green line means the model performance on the images with two objects, and the red line means the model performance on the images with more than 3 objects. We can find there's a big gap between the model accuracy between the image with one object and more than two more than two objects. It drops more than 10% across all models. But if we let's see the second figure. This accuracy is the standard accuracy that I introduced before. That it only takes this one label as a ground truth. What if we take all these 4 labels as ground truth? So if the model predicts the label that matches the label of any object in the image, we can find that the multi-label accuracy on images with more than 2 objects is rise, and this drop is essentially disappears. We can find if we use the traditional accuracy, the performance is the orange line, and if we regard any object in the image as the ground truth, the performance is the green line. So it illustrates that the top one, the traditional accuracy is not exactly represent the performance of the model. But it is worth note that in the ILSVRC competition, the They also use the top 5 accuracy that take account for the most of the object confusion, multi-object confusion. But the top 5 accuracy may overestimate the model performance because in the metric of top 5 accuracy, it means that let all the models to predict 5 labels. If one of the label is the ImageNet label, it is regarded as correct. It can take account the multi objects, but we can find that the top 5 accuracy on multi-object images is higher a lot than the standard accuracy. Is higher a lot than the full test accuracy. It means that it's not very accurate, and it also account for the top. Let me introduce the top 5 correction first. The top 5 correction means the model predicts the label that the ImageNet label was not the top prediction of the model, but was in the top 5. It means the model predict the ImageNet label in the in top 2 to top 5. So it corrections the accuracy. The author account for the fraction of top 5 accurate correction. We find that the top 5, the fraction of the top 5 correction is the pink line. It means the top 5 correction that correspond to the multi-object image is relative small. We find that the multi-label correction that refers to the multi-label accuracy is higher than this. So the top 5 accuracy is not very helpful to take account for multi-object confusions. And then the author analyzed the human label disagreement for these models. We find that although model suffers a sizable accuracy drop on multi-object images, they can still relatively good at prediction the ImageNet label, much than the baseline that chooses the label of one object at random. This bias could be justified whenever there is a distinct mean object in the image, and it corresponds to the ImageNet label. We find that in the left figure that about 650 label in the 10,000 label is not the label is not the mean object, but the model the state-of-the-art model can also have a higher accuracy about for these images. We can see here. It's much better than we select random object in the image. So it means the model learns learns the data distribution of the ImageNet dataset, but not exactly performs well. Because for this picture, the ImageNet label is pickle heavy. But for annotators, after annotators filtering the labels, they think the main label is the military uniform. For the models, the accuracy of the pickle heavy is this one, the red one, more than 90%. But for humans, they are prefer to predict this picture as military uniform, but not the pickle heavy. So it also consists with this picture, this figure, that models prefers to predict the label that refers to the ImageNet label, but it is not it not agree with the humans prediction. So it means that the improving the ImageNet accuracy, it may not generalize to the real world. The second experiment is to test the bias in the label validation. The goal is to, in this phase, is to understand how likely annotators are detect the incorrect samples during the image validation process. Recall that the annotators are asked somewhat leading questions of whether a specific label is present in the image, makes them prone to answer positively, even for image of different yet similar classes. We find that for nearly 40% of the images, another label is selected for as often as ImageNet labels. For more than 70% of the image annotators are select another label at least half as often as they select the ImageNet labels. So the annotators are actually select a lot of labels for images. Moreover, this phenomenon does not occur only when the multiple objects are present in the image. Even for the image with single object, the annotators are often select as many as 10 classes for the image. We can find this for the image with a single object. They may select more than 10 labels for this image in the ImageNet creation process. And we find that it is because the contains task set up in the ImageNet dataset creation pipeline. But we can find that in the second figure, it is the process that the authors proposed for the classify task. We find that if some potential label is provided to the annotators, they are subsequently to select fewer labels. It means they are not they are not so confused for this task. You can find for the images with only one object. The annotators is to the maximal number of the labels that annotators select is about 6 labels. It's much less than this more than 10 labels. It's also the same for the object, 2 objects, 3 objects, and 4 objects. This finding highlights that how sensitive annotators are to the data collection and the validation pipeline setup. It also indicates that the existing ImageNet annotation may not have been vetted and as carefully as one might expect. Here are some confusion class pairs in the ImageNet. We found that there are several pairs in the image classes that annotators have trouble telling apart. Okay, we can find that in some classes, in some similar classes, the efficient net B7 accuracy is still high. They can tell apart the Eskimo dog husky from the Siberian husky. The accuracy are very high, but for some labels, like the laptop and the notebook computer, the performance is much lower. For this phenomenon, the authors think it is because for these pairs, the image retrieval process are sufficiently error-free. That is, the overlap in the image search results for these 2 classes is not significant. For example, for the Eskimo dog, the image, the search engine may output different results with Siberian husky, but for the laptop computer, they may output the similar results, similar images to the notebook computers. So annotators' inability to remedy the overlaps in the case of ambiguous classes pairs could be due to the presence of the class that semantically quite similar, which is the problematic under the contains task as discussed before. In some cases, we find that there also were errors in the task setup. For instance, there are occasional overlaps in the classes name and the Wikipedia links. For example, the laptop computer and the notebook computer. In the right figure, we can find that this line refers to the top one accuracy on ambiguous classes. This one is the pairwise on the ambiguous class pairs. This line means that select the similar object by random. We can find that the top one accuracy for the state-of-art models is not good, then the select the object randomly. So it performs worse for these labels. Here is the title is Beyond the Test Accuracy, Human in the Loop Model Evaluation. It means that human are the author assists model performance evaluation by humans. It discusses whether more accurate model are also make higher quality of the prediction. To discuss about this problem, we need to first introduce two concepts. The first one is the selection frequency of the prediction. It means how often the annotator selects the predict label as being present in the image. And note that this metric accommodates for multi-objects or ambiguous classes, as annotators will confirm all valid labels. The second concept is accuracy based on mean label annotation. It refers to how frequently the prediction matches the mean label for the image, as obtained using the classify task. We can find in the left figure that here is the top one accuracy for the state-of-the-art model, and this one is the selection frequency for the predict label. It means the label select how often the label is selected by humans, by annotators. And this one refers to how often the ImageNet label is selected by humans. You can find that with the increase of the top one accuracy of the model, the humans are more likely to select the predict label other than the ImageNet label. It means the more accurate model is to predict a more a close prediction like humans. Humans are likely to select the predict labels, but it also means that humans are not like to, in sometimes, not like to select the ImageNet labels like the picture that shows before, with the military uniform and with the military uniform. We observe that the annotators are most equally to select the predict label with the ImageNet label. This indicates that model prediction might be closer to what a non-expert annotators can recognize as the ground truth than the accuracy alone suggests. So it means that we are at a point we may no longer be able to easily identify the extent to which further gains in accuracy correspond to such improvement as opposite to the model is simply matching the ImageNet label distribution, but it means that some model is to overfit the dataset of the ImageNet to improve the top one accuracy as the evaluation metric but in fact, it's not better performed in to the real world task. Let's make a conclusion of this paper. The first one is the author think that the pipeline design of the ImageNet dataset can lead to certain semantic errors, such as a wide presence of images with multiple valid labels and ambiguous classes. The second is the author finds that the deviation significantly impact what ImageNet trained models learn and how we perceive the model progress. For instance, the top one accuracy often underestimates the performance of the model. Such issue make it clear that measure accuracy alone gives us only an imperfect view of the model performance on the underlying object recognized task. The third one is also find that the model that are more accurate on ImageNet also tend to be more human-aligned in their errors. It indicates that we are at a point where we cannot easily gauge whether further progress on the ImageNet benchmark is meaningful, or it is simply result of overfitting the benchmark. The fourth is that the authors finding that highlights an inherent conflict between the goal of building a rich dataset that captures the complexity of the real world and the need for annotation process to be scalable. So developing a annotation pipeline that better captures the ground truth while remaining the scalable is an important avenue for the future research. Okay, thank you for your listening.
Thank you for your presentation. And now we can answer questions. You can raise your hand in the chat. Gonzalo, please.
Hello, can you hear me?
Yes.
Yes, good. So my question is about the problem analysis the problem analysis you presented here in your presentation. You mentioned like the multiple objects in one image and biases. But I was concerned about, I don't know if this additional problem, this is why I want you to comment on that, is when you see an object in the image, but it's not complete. So this is a problem also from this type of algorithms, and it's a curiosity I want, and I don't know if it is contemplated also within this analysis. I mean, for example, if you see a guitar without strings, still a guitar, or a car without wheels, is still a car. I mean, this type of questions when I see problem analyzing or tagging some images.
Sorry, but I cannot hear your question clearly. Can you?
So the question.
Input this in the text in the chat?
Okay.
Okay, thank you very much. Because the noise is the voice in the garden room is not good.
Okay, then I will.
Thank you very much.
Can you repeat the question now?
I will repeat it by text, I think. Yeah, I'm writing it down.
Okay.
Okay, thank you very much.
Of course, I have an observation for the natural language people, right? Really, here with this work in ImageNet, excellent.
这个感觉有点糊，就是那个回声根本听不太清。
嗯。
You can see. So I don't know. I was thinking that maybe Gabor. I have a lot of questions to ask, but I was wondering whether the natural language people had anything to say.
Okay.
So it's not a question to you.
Because I only hear about the acoustic guitar and maybe the ImageNet creation pipeline.
Okay, good. Gabor says there is no question. Okay, no problem. So let's wait for Marcelo then.
The same path of objects can be sent. Oh, I see. You mean a car without a wheel can be attacked with a car in the ImageNet creation pipeline? Okay, thank you. It maybe will be regarded as this it as the label because sorry. Can you see this slide? Yeah, okay. Because when the car without the label may be also may be searched by the search engine, and it's judged only by the annotators whether it is a car or not. But if I am a annotator, maybe I will think it is a car. But for someone, it may be not. So it will have a selection frequency. It means the how many annotators think it is a car or not. Uh, if it over a threshold, it will be regarded as a car. So also it's the same for the guitar without the strings. In the ImageNet creation pipeline, it may be regard the it may be lead to this phenomenon. Okay,
Other questions?
okay, thank you.
Okay. Xiaoye?
I want to ask a question about the ImageNet labels. I want to know where we can find these labels. We can find in some open resource or we should annotate by ourselves. Like the Xiaolei collect the labels from us, and it is should be image label or the man label. You mentioned.
Okay. For the ImageNet label, we can find it at the open source resource. They have the paired image and the label pairs. So for each image, they assign a label for this, and we can get it open sourced. For you mentioned the main label and the other label, it is annotated by the authors of this paper. They also open source this resource online, but it's only about 10,000 images. Because for the ImageNet dataset, it contains more than I think 14 million images. But for this paper, they only allotted for 10,000 images.
Oh, okay, thank you.
Thank you.
And Wang, please answer question.
Hi, Total. So I have a similar question to Marcelo. So when I was doing the task and by Xiaolei, I saw some images with like, for example, a guitar cake in the picture, but still, I don't know how does this recognize? It should be recognized as a guitar, or it's not unrecognized.
Sorry.
So my question is, if this also happened to the ImageNet, so how the users will give the labels?
Sorry, can you repeat the questions? Because I switched the speaker of the device, it is more clear now. Would you mind repeating your question?
Okay,
Thank
but
you.
can you hear me?
Yes, it's good.
Okay, so my question is, what about the pictures? For example, a picture with a guitar cake in the picture. So when the user give the labels to these pictures, how do they give the labels? Like it should be a cake or should be a guitar? I guess I have the same questions when I was doing the tasks sent by Xiaolei.
Oh, I know. For the you mean that a picture contains a guitar and a cake, and
Not a guitar and a cake. It's like a cake in guitar shape.
a cake in guitar shape. For if use the ImageNet creation pipeline, they should first give you the label about a guitar or a cake and the picture. You just to validate whether it is a guitar or cake. You just need to say yes or no. But if you you are undertake a classify task, you that you should judge whether you should give a label for the picture. So it depends on the whether it gave you the label of the picture, or you need just need to validate.
So they give you optional labels, but also like descriptions.
Yes.
Okay, so okay.
Sorry, may I say something? Sorry.
Yes.
Okay, maybe Wang, I can answer your question. In the ImageNet, in the ImageNet, we will give the label first, and the annotators only just choose the some images have these labels. I mean, you can find some images and you can choose if the images have some object in about the labels. If its answer is yes, you will choose it and they finish the annotation. But in our classification, we don't want to give the labels. We just want to give some description about the object, and you choose the object based on the description, the definition, and I mean, in our task, the genus and the differential. For this case, we will find that we can classify the object without the labels. If you don't know the labels in our task, if you didn't know the object, I mean, know the name of the object, you cannot classify that because you have no idea about what is it. But in our task, if you find some definition, you can classify the object, I mean, like this. But in the ImageNet, if you don't know the labels, don't know the object, you cannot classify this. And it will give us some confusion, maybe like that. May I answer your questions?
Okay, so I guess I see the difference between your work, our experiment, and theirs, right?
Yes.
Like theirs, they just have to validate if it is correct or not. But in our cases, we need more descriptions.
Yes, because for different cultures of people, we can classify based on one classification rules. But if for the people with different background, different culture, they maybe have some misunderstanding with one labels.
Okay, thanks.
Okay.
Okay, thank you for Xiaolei, and thank you for Wang Yi.
Is there anybody want to ask more questions? Okay, I think this seminar can be stopped here, and thank you for all of you attend this seminar. Thank you. See you next time. Bye.
Thank you.